Welcome to this presentation on the functional safety and security aspects of CANxl. Over the next 20 minutes, we will walk through how CANxl addresses both functional safety and cybersecurity at the protocol level, what role higher layer protocols and controller hardware play, and how the CANsec security extension protects CANxl networks with minimal performance overhead. Whether you are evaluating CANxl for a new design or comparing it against other in-vehicle network technologies, this session will hopefully give you a solid technical foundation. Modern connected vehicles demand ever-increasing bandwidth from their in-vehicle networks. But bandwidth alone is not enough. We also need functional safety, which includes error and fault detection, fault handling strategies, and fault tolerance for high availability. On top of that, we need security, data integrity, data privacy, and data authenticity. CANxl accepts this challenge head-on. It is designed to deliver higher bandwidth while simultaneously strengthening both safety and security. In this presentation, we will focus on the data link layer and above. There are excellent companion presentations that cover the physical layer in detail. So let us begin with the functional safety side of CANxl. The good news is that CANxl does not start from scratch. It builds directly on the proven safety attributes of classical CAN and CANfd, protocols that have been deployed in hundreds of millions of vehicles. But CANxl also addresses the new challenges introduced by longer payloads, up to 2048 bytes, and faster data rates. These longer frames change the error probability landscape, and the protocol has been carefully designed to maintain the same level of safety assurance. Let us look at the specific features that make this possible. On this slide, you can see the structure of a CANxl frame, which consists of an arbitration phase, control fields, a data payload, a CRC section, and an acknowledgement sequence. Let me highlight the key safety-relevant features. First, reliable frame reception. Every frame must be explicitly acknowledged by at least one receiver. If no acknowledgement is received, the transmitter knows the frame was not successfully delivered. Second, protection against random bit errors. CANxl uses a 32-bit frame CRC, referred to as FCRC, which maintains a Hamming distance of 6, meaning it can detect up to 5 random bit errors in a single frame. This is the same detection strength as classical CAN and CANfd, but applied across much longer payloads. In addition, CANxl introduces a second CRC, the 13-bit preface CRC, or PCRC, which protects the header and control fields. This allows errors that occur early in the frame to be detected before the entire payload has been received. Third, deterministic, non-destructive arbitration. As with previous conversions, arbitration is based on a priority identifier, where the node transmitting the numerically lower ID wins bus access. CANxl enhances this mechanism with the 32-bit acceptance field, or AF, which provides additional classification bits and reduces the probability of ID collisions. The SDT and VCID fields, which appear earlier in the frame, further increase the likelihood of detecting collisions sooner, before significant bus time is wasted. Clock synchronization is critical in any serial bus protocol. CAN keeps all nodes synchronized through periodic signal transitions within each frame. It starts with the start of frame bit, which provides the initial reference edge. Then bit stuffing ensures that regular transitions continue throughout the arbitration phase, giving receivers frequent opportunities to resynchronize. CANxl extends this principle for its high-speed data phase. After the speed transition, fixed position stuff bits maintain synchronization even at the faster bit rate. The ADS, FCP, and DAS fields contain fixed bit patterns specifically designed to ensure reliable synchronization at the points where the bitrate switches occur. CANxl also preserves the fault confinement and error isolation mechanisms from classical CAN. Error counters track the behavior of each node. When a node experiences persistent faults, it transitions from error active to error passive, and eventually to bus off, effectively isolating the faulty node from the network. So this raises an important question. Are these protocol-level safety features sufficient for real-world automotive applications? Let us explore that next. The answer is not entirely. While the protocol provides strong baseline protection, certain error patterns, such as burst errors affecting multiple consecutive bits, can occasionally exceed the detection capability of the CRC alone. This is where higher-layer safety protocols come in. CANopen Safety, defined in CIA 304, is a well-established example. It operates on the black channel principle, meaning it does not rely on safety-rated hardware. Instead, all safety mechanisms are implemented in software, running on top of standard CAN controllers. Here is how it works. After each data frame, a second frame with an inverted copy of the payload is transmitted. This redundancy catches burst errors that may have slipped through the CRC check. An additional end-to-end CRC provides further error coverage across the full communication path. Sequence counters ensure that no frames are lost, duplicated, or delivered out of order. And tight time monitoring, including the safety cycle time and safety-related validation time, detects network anomalies and timing violations quickly. This brings us to the next question. If higher-layer protocols like CANopen Safety can handle safety without specialized hardware, does that eliminate the need for safety-enhanced CAN controllers? Before we answer that, let us consider what a CAN controller actually contributes to functional safety. First, the controller is the component that enforces protocol-level safety features. Non-compliance with the protocol specification or uncovered verification gaps can lead to increased safety risks. A robust controller implementation is the foundation everything else builds on. Second, the controller enables early error detection and localization. It can identify faults at the bit level and report them to the application layer with detailed status information. Third, and this is important, a well-designed controller fails gracefully. It does not halt the bus unexpectedly. Instead, it transitions through well-defined error states and provides the upper layers with the status information they need to make informed decisions. These capabilities make the controller a critical element in the overall safety architecture, even when higher-layer protocols are present. Now let us look at what happens when we take controller design a step further. Errors inside the controller itself are a real concern. Silicon devices experience transient errors from electromagnetic interference or single event upsets, persistent errors such as bit flips in configuration registers or state machines, and permanent errors like stuck-at faults or bridging defects. The consequences can be significant. Corrupted frames trigger retransmissions, which increase latency and make communication timing non-deterministic. Bandwidth is wasted on repeated transmissions. In the worst case, a faulty node may enter the bus-off state and become unavailable, or it could continuously interfere with the bus, making the entire network unusable. A fault-tolerant controller, one that continues correct operation in the presence of internal errors, directly addresses these problems. It improves network availability, reduces communication latency, and preserves bandwidth even under fault conditions. So how do we build fault-tolerant controllers? Let us examine the key techniques. There are three primary techniques used to build fault-tolerant controller hardware. The first is modular redundancy. In dual modular redundancy, or DMR, you instantiate two identical copies of the hardware module running in parallel. Both receive the same inputs, and their outputs are continuously compared. If the outputs differ, a fault has been detected. DMR can operate in lockstep mode, where one path is delayed by one or more clock cycles, reducing the probability that a single transient event affects both modules simultaneously. Triple modular redundancy, or TMR, takes this further with three parallel instances and majority voting. TMR not only detects errors, but corrects them on the fly, and it can identify which specific module has failed. The second technique is redundant data encoding. When data is written to memory or a register file, an error detection code is computed and stored alongside it. On read, the code is recalculated and compared. SecDec ECC, which stands for Single Error Correction, Double Error Detection, error correcting code is the most widely used scheme for memory protection. It can correct any single-bit error and detect any 2-bit error. For control and status registers, simpler parity-based protection is typically sufficient. The third technique is built-in self-test, or BIS. This addresses a subtle but important concern. What if the error-checking logic itself is faulty? BIS allows the host processor to inject known errors into the protected modules and verify that the error detection and correction mechanisms respond correctly. This periodic self-validation ensures the safety mechanisms remain trustworthy throughout the system's operational lifetime. Let us summarize the functional safety story before we move on to security. At the protocol level, CANxl implements a comprehensive set of safety features: reliable frame reception with mandatory acknowledgement, deterministic non-destructive arbitration, strong CRC protection with both the frame CRC and the preface CRC, fault confinement through error counters and node state management, and robust clock synchronization across bitrate transitions. Higher layer protocols like CANopen Safety extend these protections further. They add end-to-end redundancy, sequence monitoring, and time-based supervision, all without requiring specialized hardware. And for the most demanding applications, safety-enhanced CAN controllers with modular redundancy, ECC-protected memories, and built-in self-test provide early error detection, graceful failure behavior, and improved availability under fault conditions. Now, let us shift our focus to the security side of CANxl. CAN was not originally designed with cybersecurity in mind. Its open broadcasting nature means that every node on the bus can see every message. This makes CAN networks inherently vulnerable to several attack vectors: spoofing, where an attacker injects forged messages; sniffing, where an attacker passively reads all bus traffic; replay attacks, where previously captured legitimate messages are retransmitted; and denial-of-service attacks, where an attacker floods the bus to prevent legitimate communication. These vulnerabilities create real risks. They can compromise user safety if critical control messages are manipulated, and they can result in financial losses through intellectual property theft. CANsec is the security extension designed to address these threats for CANxl. Rather than inventing a new security architecture from scratch, CANsec leverages MACsec, the well-established and proven security standard used in Ethernet networks. The standardization of CANsec is currently in progress under CIA 613-2. Let us look at how it works in practice. When CANsec is enabled, the structure of the CANxl frame payload changes. The SEC bit in the header signals that security is active. Inside the payload, 3 new elements appear. First, a CANsec header that specifies the security options in use. Second, the data payload itself, which can be optionally encrypted. And third, an integrity check value, or ICV, which serves as the authentication tag. This structure follows the same pattern used by MACsec in Ethernet networks. The cryptographic algorithm is AES-GCM, which provides both authenticated encryption and integrity verification in a single operation. The system supports both 128-bit and 256-bit key sizes. Key management, including key distribution and rotation, is intentionally left to the application layer. This keeps the link layer security mechanism clean and allows implementers to choose the key management approach that best fits their system architecture. Moving on, let us look at how CANsec organizes secure communication across the network. CANsec introduces the concept of security channels. The CAN network is logically divided into independent security channels, where each channel is a group of nodes that share the same cryptographic key and freshness value. Nodes within a security channel can communicate securely with each other. The security channel for each message is identified in the CANxl header, so receivers know which key to use for verification and decryption. This design is elegant because it allows different groups of nodes on the same physical bus to operate at different security levels. Safety-critical powertrain messages might use one security channel with 256-bit keys, while less sensitive body control messages might use a separate channel or even remain unsecured. This flexibility mirrors the VLAN concept familiar from Ethernet networks. Now, an important practical question: what is the performance cost of adding this security? The CANsec header and the ICV authentication tag add overhead to every protected frame, which reduces the effective payload bandwidth. The chart on this slide quantifies that impact across different payload sizes. For large payloads above 512 bytes, the bandwidth overhead is negligible, well under 4%. But for smaller payloads, the impact is more noticeable. With an 8-byte payload, comparable to classical CAN, the effective bandwidth drops by roughly half. At 64 bytes, in the CAN FD range, the overhead is around 20%. The good news is that above 128 bytes, the overhead falls into single-digit percentages, and above 960 bytes, it is less than 2%. But bandwidth is only half the story. The AES GCM encryption and decryption operations themselves take time. On an ARM, Cortex-M4, running at 200 MHz, a highly optimized software implementation requires between 200 and 600 clock cycles per byte. For a full 2048-byte payload, that translates to 2 to 6 milliseconds of processing time, not including data transfers to and from the CAN controller. For automotive applications with strict real-time constraints, that latency is unacceptable. The conclusion is clear. Hardware acceleration for CANsec is essential. Let us see what that looks like in practice. This slide shows the results of a real measurement using a CAN XL controller with an integrated CANsec hardware accelerator. In the test setup, the controller and the embedded RISC-V processor operate at 200 MHz. The CAN data rate is 20 megabits per second with a 128-byte payload using AES GCM with a 256-bit key. The timing diagram tells the story clearly. Writing the frame to the controller takes about 0.54 microseconds. The CANsec authenticated encryption completes in approximately 2.7 microseconds, and the bus transfer itself takes about 73 microseconds at this data rate. The critical observation is that the CANsec processing time is dramatically shorter than the bus transfer time. This means the encryption and decryption operations can be pipelined with the bus transmission. While one frame is being transmitted on the bus, the next frame's security processing can happen in parallel. At lower transmission speeds or with larger payloads, this ratio becomes even more favorable. Let us see what this means for back-to-back frame throughput. This is where the hardware acceleration really pays off. On a busy network with continuous back-to-back frames, the CANsec processing for the next frame is performed entirely, while the current frame is still being transmitted on the bus. The result is remarkable. There is zero additional latency from the security processing. There is zero extra bandwidth consumed beyond the CANsec header and ICV fields themselves. In other words, once you have hardware acceleration, the only performance cost of CANsec is the space occupied by the security metadata in each frame. The cryptographic computation itself is completely hidden behind the bus transfer time. This makes CANsec practical even for the most latency-sensitive automotive applications. With both safety and security covered, let us bring it all together. 3 key takeaways from this presentation. First, CANxL preserves and enhances the functional safety attributes that have made the CAN bus the backbone of automotive networking for over 3 decades. The protocol-level protections have been carefully extended to handle longer payloads and faster data rates without compromising safety assurance. Second, CANsec brings the proven MACsec security architecture to CANxL, providing authentication and optional encryption with minimal performance and latency overhead, especially when paired with hardware acceleration. Third, purpose-built CANxL controllers and CANsec accelerators are the foundation for efficient real-world deployment. They combine protocol compliance, fault tolerance, and security processing into a single integrated solution. Let me briefly introduce the specific products that implement these capabilities. CAST offers a safety-enhanced CANxL controller designed for ASIL-D applications, the highest automotive safety integrity level. The controller implements SecDec ECC protection for all internal memories and parity protection for control and status registers. Critical functional modules, including the CRC generators and checkers, error counters, and the protocol engine, are implemented with selectable dual or triple modular redundancy. a built-in error injection facility, enables comprehensive self-test coverage. This controller is built on over 25 years of experience, delivering CAN IP cores to more than 200 customers worldwide. Alongside the controller, CAST also offers a dedicated CANsec hardware accelerator. It integrates tightly with the CANxl controller for optimal performance, but it is also designed to function as a standalone accelerator with third-party CAN controllers. This gives system designers the flexibility to add CANsec capability to existing architectures. Thank you for watching. I hope this presentation has given you a clear understanding of how CANxl addresses both functional safety and cybersecurity for in-vehicle networks. If you have questions about the protocol, the controller architecture, or the CANsec accelerator, contact us via the email below and we would be happy to discuss them with you.